Day, and what I'd like to do today is sort of follow on from Ben's first Antarctic lecture, so it's quite a generalised topic, and I've called it Going to Extremes, and I want to talk about the sort of the extreme environment and what that's like. And so the stage is moving a little bit. If you see me over there, I'm just making sure that nothing's wiggling away from me. Alright, let's try this. Okay. So last time I introduced you a bit about myself and where I'm from and sort of my connection to Antarctica. So I thought I should probably prove it. And I found some photos of me in the wild, and it turns out I don't take a lot of photos of myself. And I'm always wearing a baseball cap. So if you see some crazy lady standing outside on a deck and it's blowing, and an orange cap, that's going to be me. Of course, given how many of us there are, that might make me a bit tricky to find, so you'll see me in one of these hats. I look like a ridiculous ginger gnome. So there's a couple of photos. The bottom left is me standing actually not too far from Mount Erebus, which is something I'll talk about today. And of course a shout out to all the Kiwis, and this is our Scott base. And so it's this relatively small Antarctic base with these lovely green painted sort of containers. And so that's kind of what it looks like. And this is me doing my best Where's Wally impersonation. I'm in this photo. Can you see me? Oh, excellent, some of you have. I wasn't trying to hide. So this is in the McMurdo Dry Valleys, and I'm standing on the edge of the Taylor Glacier. And this was an extraordinary trip where everything was melting. It was +8 degrees at a place where the mean annual temperature is -18. We had really hot, strong winds, and suddenly there were waterfalls and rivers everywhere. It lasted for a few days, but what's happening in this photo is it's actually sort of cut in to the side of the glacier here, and was just melting away all this water. And so when you've got an environment that's made of ice, it reacts really quickly as soon as you get into positive temperatures, and it's a profound change in sort of the landscape. Now, it's not to say that these rare events occur entirely as a consequence of human warming, but it is also to say that they do occur in sort of the broader envelope of climate. What I really want to talk about today, though, is what makes Antarctica extremely unique. So this is a photo taken in East Antarctica in the New Zealand sector, and this is one of the wildlife that we see there, so it's one of our marine birds. Now hopefully some of you had a chance to learn up on the birds of Antarctica with Ben this morning. This happens to be a skua. And where I was in Antarctica, it was pretty much the only wildlife we saw. In the dry valleys of Antarctica, it's very cold, there's not a lot of water or food, and so we only see these occasionally come in, reasonably just to have a nosy. They're quite aggressive birds, and when you see them in and around the rookeries, they're always trying to get themselves a penguin omelette. They're very, very cunning birds. So what I thought I'd start with about the extremes of Antarctica is thinking about its size. Right, so most of us probably went to a school where in one of our classes there was a map, or maybe you had the map in the front of the atlas. I'm aging myself here. I don't think anybody who's under 30 knows what an atlas is. It's all pinch and pull these days. Right, so this is one of the projections. This is the Robinson projection. You might be more familiar with the Mercator projection, or maybe a slightly distorted Peterson's projection. And how we mapped the world was entirely around navigation, how to get from A to B. We needed to know where we were on the planet, and we could use the stars to do that. And we also needed a way of understanding longitude. So often we used initially clocks, time, to tell us where we were relative to sunrise and sunset. And so for most of our lives, or at least if you were as young as I am, you saw the world like this. And there was this fluffy white thing at the bottom for which you have actually no idea of its size. Now there's plenty of other distortions that happen in these as well. They're drawn so that the shape looks the right, and there will be some creative license taken with how big different places are. And so what I would get you to think about, right, that these maps are a compromise, or perhaps even all maps lie, is that we could conceive of another way of mapping the world. So this is the orthograph, and it breaks down these geographic ideas of north and south, which propagate certain ways of thinking about the north being more developed, the south being less developed. It holds in lots of the prejudices of our past. Now for this, the challenge of course is finding where you are, but it's one of the few maps that actually projects the shape of places and their size equal across the planet. And it actually challenges the way we conceive of the place in which we live. We can now see how big the Pacific Ocean is, which, unless you grew up in my part of the world, was always on the end of your maps, and you had the Atlantic in the middle. And it's drawn by a series of triangles, so we've got now distorted lines of longitude and latitude. But here we can actually see what Antarctica looks like. Right, we're not using a polar projection just to look at Antarctica. We can now see it in relation to other places. And of course we can have some fun with these things. So Antarctica is our fifth largest continent. It's the one with the highest mean elevation, so that is including its ice surface. Its elevation is well over 2,000 metres, 7,600 feet. If we were to look at the diameter for it, it's something like 4,500 kilometres, for an overall area of around 13.7, 14 million square kilometres. And so we can now project these things relative to other land masses. Right, we've been sailing down the south, along the coast of South America, and we can now see the size of how Antarctica looks relative to South America. Obviously South America is a little larger. But we can also have a look at it relative to Australia. And inside there you'll see New Zealand. Think of New Zealand as being about the same size-ish as the United Kingdom, as the Archipelago of Japan. They're all pretty similar. And we can also see that in terms of the contiguous USA and Western Europe. And if we think about the scale of those places and how we would travel across those, we now get a sense of the scale and the magnitude of trying to traverse Antarctica. And perhaps the boldness of Shackleton's endurance expedition. This idea that he was going to be the first to lead an expedition across from West Antarctica to East Antarctica. And what an extraordinary undertaking that would be. That he was going to start in the Weddell Sea, which is reasonably not too far from where we are going on the peninsula, so a bit more east. and it was going to cross the Transantarctic Mountains through the South Pole and end up on the other side. Extraordinary, bold ambition. Wasn't successful, but it was bold. And so now we can think about just how large a place we're talking about, that it's no longer this white fluffy edge on the bottom of our maps. And so Antarctica itself is this lost continent. And we describe it as having East Antarctica and West Antarctica. And the division between those is the Antarctic mountains.
Bà phải nói gì?
Don't confuse me with
Australia.
That go through here. This is the Ross ice shelf at the bottom. This is the Romford ice shelf at the top. Here's the peninsula. And so if we followed that arc of mountains, we'll be able to divide it into west and east. And the thing between the two is that the amount of ice is quite different between them, and how it's going to change are quite different as well.
Từ đấy đến
But in
năm
general,
nước kìa.
the average ice thickness across
Nhớ
the
nhớ hồi đó
entire
mấy người đến
continent
Úc không? Đến
is
Úc mà đi
still
qua Mỹ á.
about
Em đến Úc mà qua Việt Nam nó hiền lắm.
2.5 meters.
Ở chỗ gần nhà em có một cái
kilometers.
trường
And we know
văn hóa
this
quân
because
đội nó
they
dạy cho
use
lính Úc á.
airborne radar to map ice thickness.
Nó dạy tiếng Việt cho lính Úc. Nghe ở đó bà già bà sợ lắm, không có cho
But so what we can now do then is if we know something about ice
bà sợ.
thickness,
Bà sợ.
and we can
Tại vì
determine
gái
that
này đi
using
làm
satellites and
điểm
radar,
mà.
we can create a map that tells us about ice thickness. And this is actually what you're looking at. I know it's in very pale pastel colours here and the legend's impossible, but our areas that are pink, they're less than 400 metres. Those areas of
Ông đi ra rồi ông chạy
green
lẹ lắm.
are more than 4,000 metres, and there's another sort of pink that you're seeing. It's a different pink up here. Terribly useful. Well done, cartographer. That tells us it's about over 3,000 metres. So, our thickest part is not the South Pole. Right, it's actually often what we'd call dome sea out around here somewhere. There's another thick part up here as well. West Antarctica is a little bit different. It's not quite as thick, and that ice mass actually discharges to the ocean, so it's also interacting with quite a lot of water at its edges. Now that's true of East Antarctica, but for the most part it's sitting on bedrock, and there's only small amounts of area that are interacting with the ocean. But for West Antarctica, we have our ice that's built up over time, and at the moment our bedrock, as it's dark brown area here, is actually below sea level. So that means if water is able to get in underneath the ice above that ledge of rock, so we've got in here, it means that water could flow into the bottom. And that means for West Antarctica that the ice sheet is melting in two directions. It's melting from the top, or we'd call it sublimation. That is water vapour being lost directly from ice. And it's melting at the bottom. Because the ocean is salty, it's a little bit warmer, and so if there's interactions at that, it's going to melt in both directions. So that means that West Antarctica is actually quite vulnerable to changes in sea level, but also changes in ocean temperature. Antarctica, of course, wasn't always the way it is now. And like I described in the last lecture with plate tectonics, I was kind of setting this up for this lecture a little bit. This idea that we have a series of plates of crust that are moving around the mantle, like trying to chase the sugar coat on your creme brulee, all right? It's ice moving around on this liquid surface. And part of those movements has been the migration of the landmass of Antarctica from sort of mid-latitudes down towards the pole. And so up until 160, 200 million years ago, it was a part of the Great Southern Land, Gondwana land. And then the plate tectonics started doing some things, moving it away, drifting slowly further south. But for all of that time, the continent was actually temperate. It had forests, mammals, swamps. And even by the time it got to its present location, it was still able to hold on to those cool, temperate forests. But what happens is as it's moved further away and our plates have reorganised, it's found itself cut off from everywhere else. And so suddenly there's an ocean that can start to move around, the opening of the Drake Passage. And that meant that water could then move freely around the continent. And it kind of cut it off from the rest of our atmospheric processes of moving energy around. And so that movement towards the pole, the opening up of that ocean space, is what starts to begin the glacial history of Antarctica. So here's just a simple cartoon that sort of shows its geographic location over time. Right, so we can see about 160 million years ago, it's a warm period. Now, Antarctica is painted white here. It's just so you can see it. It's not actually glaciated. It's warm. It's connected to Australia here and parts of South America and Africa. By about 70 million years, it's starting to drift towards the pole. Australia is still pretty close, but we don't have that wide ocean forming yet. By about 45 million years, that gap starts to open up. And so we start to see a continued drift south. And it's only reasonably in the 35 million years where that cooling really starts. And so over that time period, we're moving from the Southern Ocean being relatively warm, 18 degrees, to relatively cool to about 12 degrees. And now, in fact, it's much cooler than that. And so we can look and we can reconstruct this by, if we have a chance, to look at the types of rocks that are in Antarctica and how they may be connected to other places. The challenge is, if you've got a continent that's covered in ice, there's not that many places where you can do that. And so a geologic understanding of Antarctica in terms of what rocks it's made up of and how that connects to other places is from these tiny little pockets of exposures in oases, areas where there is no ice accumulation, or where the mountains are but large enough to pierce through. And so the first sort of continental map of the geology of Antarctica has been published last year. This is by Simon Cox, who works in GNS in my hometown. He's a good friend of mine. And this was published in a prestigious journal late last year, of the first time that all the different scientific organisations have come together to create one coherent geological map of Antarctica. And so this is what it looks like. Right? These are the areas we can see. So we can see the peninsulas are incredibly important for us for that. It's associated with a rift system where the plate is thinned, and it's mostly volcanic rocks. So new rock that's been generated. We can see the little pockets in through the Transantarctic Mountains where it's mostly metamorphic rocks. Beautiful granites, diorites, granodiorites, lovely, different geology entirely. And so there's so much that we still don't know about what's there, but we can piece it together from these little areas. Now, one of the things we do have are volcanoes, and some recent work looking at the radars and the distortion of the ice suggests there's probably around 130 remnants of volcanic cones, mostly in West Antarctica, but we do have 2 active volcanoes. And recently what's happening here is that these volcanoes are emerging from the plates subducting in and around the South American plate, the Antarctic plate. It's a little Scotia plate that kind of moves through the Drake Passage, and there's also a little South Shetland one. And so they're kind of sticking together and pulling down those plates, and so we do get a few earthquakes associated with that through the Bransfield Strait, and those earthquakes are generally relatively quite shallow, they're not very strong, and they're associated with the active volcanism in Deception Island. The other volcano, and I'll come back to Deception Island, is that of Erebus. Now, Erebus is sort of a special place for New Zealanders for other reasons, but it is the main active volcano. It's one of the 2 volcanic cones on Ross Island, so this is the little island here. Mount Terror is dormant. And what we've got is a really interesting alkaline volcano system. It's got a crater, it's got a lake, it's got lots of fumaroles, and you see it puffing away. And it's a really interesting place in terms of specialised microbes, and a lot of scientific work for that particular type of a volcano is done there. It was first discovered by James Ross in 1841, who described it as emitting flame and smoke in great profusion. The first person to ascend Erebus was associated with Shackleton's failed race to the South Pole in 1908, and so Edgeworth David, who was also a scholar at Oxford University, who was the geologist from Australia at the time, was the first person to reach the peak. And he would describe that his great globular masses of steam would rush up towards the swell volume of the snow-white cloud, which ever sways over the crater. And so for them, this was a really important discovery. And it also leads us to ask questions about how we're seeing ice sheets melt. Is there a chance that there's volcanoes underneath these and the heat associated with that, and is that what's melting the ice sheets? And there are subglacial volcanoes. They're not erupting through the ice, but they are warm, and there is a transfer of earth heat to the ground underneath them. And they have a localised effect, but it in no way explains the changes in ice over time. We said the other volcano is that it's Deception Island. It's certainly the most active volcano over the last 12,000 years. It's got about 30 explosions since it formed. So in the geological papers, they would describe this as horseshoe-shaped. I think it looks toilet seat shaped. So it's a collapsed caldera. So basically when it exploded, the cone collapsed in on itself. You've got about 90 metres of water depth in the harbour in here. Got a couple of permanent ice cones. It's about 600 metres, 500 metres above sea level. And it's not described as active, but rather restless. It's the nuance of geology for you. So at last wiggled, shall we say, it's going to be restless in the 1990s. and then the previous sort of volcanic activity was in the 1970s. Actually the same time as Erebus, but unrelated systems. And the other really extremely awesome thing about Antarctica is that it's also one of the best places in the world to find meteorites. And there's a couple of reasons for that. One, it's incredibly cold, and so our weathering processes, how rocks break down to make soil, are really, really slow. So if something's extraterrestrial fallen onto our ice sheet, it's going to get trapped in the ice, and it's not going to wither break down. So some of our most pristine examples of rocks from elsewhere in Antarctica. And the first one of those was in fact found by Douglas Mawson, an Australian geologist and extraordinary explorer in Antarctica in sort of the heroic age. If you ever get the chance to read Mawson's diaries or his journey in Antarctica, it is a lesser known but extraordinary story of survival. And in fact he is one of the few explorers of the heroic age who made it through to old age. And in fact he was retired as a professor in South Australia at a very fine age. And one of the reasons why people get so excited about meteorites here is not just the number of them, so more than 25,000, but we can also use some glaciology to figure out where to find them. And so it doesn't matter where they fall on the continent, that ice is going to move and flow away to the coast. And there are areas where ice is forced back up to the surface. So it's an area where it's losing volume, it's melting. And that presents as blue ice. So it's not fluffy and white. And that's where you find most of these meteorites. And so you can see this example here. You've got a ridge underneath the glacier, your ice is forced to flow up, and this is where they all accumulate. And of course, rock nerds walk around and look at all the different brown and dark brown and black rocks and go, ooh, that one. I'm not that good at geology to be able to do that. But this is what it looks like, and they sort of put flags up and mark where they are. And so there are entire expeditions to look for that. Now the other part I want to talk about, of course, is climate. As we continue our journey south, it's going to get a little cooler. And what's happening is that we're moving into an extremely different climate. Now it's of no surprise to any of you that Antarctica is cold. There's all that ice there, duh. But it's also extremely windy and extremely dry. And all of those things together make it very, very reflective. So a lot of the energy that's coming in gets reflected immediately off that white surface. So it's also not absorbed. So as we're moving across the Drake here, we're moving away from this westerly system and into this series of what we'd call subpolar lows. And those subpolar low pressure systems are a consequence of the cool air moving away from the centre of the continent toward the coast, and it creates this low pressure system. And we have this sort of series of cyclones that keep circumnavigating Antarctica. So when we look at the climate, we've got lots of different places where we can see how this is distributed. So of the continent of, how to say, is 13.7 million square kilometres, these dots represent all the scientific bases. And it might be a bit hard to see where you are, but the The stars are the ones that, even I can't read it on the screen. No one's going to actually say that to me. Would be year round, and the little open ones are seasonal, so that is their summer bases. So we've got a series of bases here, and there may be some places you've heard about. So the first one is Vostok, which is an area of a Russian base. And Vostok's an incredibly important station for us because it is one of the places where we got our first ice core. So it gives us the first snapshot back in time of what the atmosphere looked like. And Vostok's also kind of interesting for another reason, that even though you've got a mile of ice on there, at the bottom there are lakes. And those lakes are connected. So under this mile of ice, it turns out we've got an entirely separate ecosystem, entirely cut off from the rest of the terrestrial processes. And it's probably been so for millions of years. So under Vostok is Lake Vostok, and there's a lot of other lakes that have been found since. So Vostok is one of our cool locations, and it's in and around here, right? So towards the deeper part of the ice, and we can plot the temperature of the different stations through these different lines. Right? So we're looking at Vostok, the dark brown line. We'll be getting into minus 60 degrees centigrade in winter, but we've got that greatest change in temperature. So in summer, it's a positively balmy minus 30.
Oh, minus 30.
There's a reason the Russians have their base there. We've also got the South Pole, right? So this little red one in the middle here, where the Americans are camped out. And so we can see the South Pole climate is perhaps not quite as extreme as Vostok. So we're looking at maybe about just shy of minus 60 in winter, and again balmy minus 30 in summer. But by far and away, most of our bases are around the coastal fringe. And so we've got an example here of Scott Base, obviously the one that I'm most familiar with. So we're going to be in the Ross Ice Sheet shelf here, and oops, gone too far. Just in here. So Scott Base will be about minus 18 in summer, minus 40 in winter. We've also got Faraday and Mizuho, which are on the peninsula. Faraday's now been renamed, and it was a British site, and it's been gifted to Ukraine. And we see we're going reasonably towards this upper part here in the South Shetlands. Our temperatures don't change very much, and they're generally in and around 0. So that means, of course, if we start to warm the environment, we're going to see those effects most acute first in the Antarctic Peninsula. And so here we can just see what that would look like if we distributed as isotherms across the continent. No surprise, cold in the middle, warm on the outside. Easy. The part they don't tell you about that, though, is that as humans we have a band of environmental conditions which are comfortable and which we can survive. And so in Antarctica the temperature could be quite pleasant, but it's what happens when we combine that with wind speed. And that has an impact on how comfortable it is and also what activities we can undertake. And so you have felt that as we went through the Beagle Channel, the boat turned around and that wind picked up, and it was much more discomforting than it had been without it. And so we call this wind chill. And when you're working in Antarctica, wind chill's a big deal. Right, you're always making sure that every bit of skin is covered up. because the wind is so strong that it easily wicks away the heat from your body, and it's very easy to get frostbite, particularly if your gloves or something get wet as well. So when we talk about wind chill, we're thinking about sort of comfort level. And so we could start here at 0
Cái
degrees
frostbite á, quắt
and
ngoài
no
wind,
wind.
wind rồi
It's
tuyết rồi này kia
relatively
đó.
comfortable, no
Yeah.
problem. Right.
You can get,
For some of
you
you,
know,
that
you
would be an
can lose your.
ordinary winter.
Mình về mình
But if
lạnh
we
quá mình không có
move
feel được nữa.
down
You can
to
lose your
minus
feeling,
10
your feet, your
and
hand.
no wind,
Rồi ba không có feel được,
it
ba
would
không
be
có cầm được cái gì, giống như là bị
it would
stroke
be
á.
very cool. If you
Có
go
đứng giỡn.
to minus 10 and strong winds, so we're now at 10 kilometre per hour, we're moving from being cool to the edge of bitterly cold. If it was minus 20, 10k winds, we're into flesh freezing. So the climate isn't changing necessarily, or at least the temperature isn't, but that wind speed is. And my experience of that is, it was actually one of the days when we were flying out from McMurdo Station, and so we're all dressed up in our 15 layers of things. Walk around like this. You can't bend to do anything. And it was minus 30, so it's perfectly pleasant. You're waiting at the airport. It's not like your experiences of waiting at your airport. Our airport is on an ice shelf. So you're literally standing around outside. It's bright white, nothing to see here. And so I looked at the thermometer on my thing. I was like, minus 30, that's fine. And then the wind picked up, and it was so incredibly uncomfortable. It delayed our flight as well, of course. But this is why we have to be careful as scientists working in these spaces, that you can start an activity and then have to make a decision about, we now have to stop because conditions will change so quickly that can imperil the entire project. And one of the phenomena that the early explorers and those that work in Antarctica often have to deal with is this idea of whiteout. And basically whiteout is what happens when you've got a relatively weak haze of snow that's sort of blowing around, and then intense light through that, and maybe there's some clouds that makes it a bit overcast. And so what happens, and this is our experience of it when we're doing some work on the McMurdo ice shelf, is that you're out there, you're doing your work, you can see the horizon, you can see the hills, no problem. And there's a little bit of cloud on there, but that's fine. So sort of rolling over, and this is Minna Bluff, that's what it's called. And then about 5 minutes later, you can't see the bluff anymore. Conditions are fine, you can still work. But if you're working in these conditions and you see those changes that quickly, you go, hang on a minute, I know what this means. Because about 5 minutes later, and this is all the skidoos now parked, you can't see anything. That's looking at the same range, right? That's looking towards Minna Bluff. And it stayed that way where you couldn't see anything at all for about 40 hours. The only thing you can do is hole up in your tent. Right, you can't go out, you can't see the horizon, you can't see the sky, you can't distinguish where that is. And so that's one of the things alongside wind chill that can make it extremely dangerous in Antarctica. Now, one of the other things, as I've described here, is that it's also the windiest continent on Earth. And it's really difficult to explain. Right? How do you take a photo of wind when you don't have any trees? And you don't have anything that's blowing around. So this is one of our field camps. It's beside the Seuss Glacier in the Taylor Valley. And it's the only thing that's moving is the windmill that's generating electricity to a battery system to feed for the science equipment that was inside the glacier. And so what we've got, you wouldn't believe, are dunes. There are migrating sand dunes of unconsolidated sand that is moving in and around in these dry locations. So not only kind of like Michael Jackson in the video leaning forward into the wind, but you are also being sandblasted. So uncomfortable.
Sandblast?
So I guess for me in those conditions and thinking about that field work, it's very much thinking of it as a lazy wind. It doesn't go around you, it goes straight through you. And in fact, in some places, the winds will average 44 miles per hour or 70 kilometres per hour. And winds have been measured well up over 200 miles per hour in the Australian sector. So it's an extraordinarily windy place. And the reason for that is all going back to that big, thick ice sheet. And so what happens is cold air sits on top of that ice. And it will move slowly down gradient away from the thickest parts. And as it gently rolls away, it picks up more air and moves a bit faster. And it increases in speed as it rolls towards the coast. And so that dense air that's accelerating is what we would call, down slope specifically, is a katabatic wind. And you get that in mountain regions, particularly if you've got glaciers. You have the katabatic wind that goes down slope. The counter to it is called an anabatic wind, which goes up slope. And we only recently see that in the oases and in the valleys. So what happens when we've got this system, right, is it means that all our katabatic wind is greatest in and around the edges. Now you'll see that's not so much an issue for the peninsula because we're not close to those big, large ice sheets, but it is really challenging if you're out east, out here, sort of Commonwealth Bay way. Now those katabatic winds also have a really important biological function, is that they blow with such regularity that they actually blow loose ice out. And so in some places you'll see that the ice on the surface of the ocean doesn't freeze and there's an open ocean. And it's because the winds, it's kind of like if you're blowing on your cup of coffee, you know, and you're forcing mechanical forcing, right? That's what you do when you're doing that, and you're exchanging heat. And our katabatic winds, as they come off the ice sheet onto the ice shelf, push the sea ice away, so you get these little polynyas, pockets of open water. And they're really biologically important because that's where the seals and the penguins are able to pop up and access the continent of the ice shelves. They're relatively salty pockets of water because as sea ice freezes, you get brine rejection, and so it becomes a bit saltier as well. So those pockets of open water, really important. Complete aside, not related to the lecture, I have some friends who do work on sea ice processes, and so one of the things they do is they go out into the ice shelf. They have little huts. They get dragged out there and they stay in these little huts for weeks on end, and they cut a hole through the ice shelf, and what they're trying to do is get to understand how the sea ice freezes at the bottom. And so you can put divers down if you're that way inclined, or we can use some automatic instruments to do that now. The problem with this is it's an open pocket of water, and the Weddell seals think all their Christmases have come at once. So your hole that's been left open for your diver, up comes a seal. Here. So, it's windy, but that wind helps for some things. The other problem is we've got mountains, and so that also helps funnel some of that wind as well. We call that's barrier winds. So what that kind of means is that you have this wind, if you've got bits of ice flowing or being blown around, anything that's in the way is going to be sculpted by that. And if you've ever read Scott or Shackleton or any of the other explorers, and they talk about their journey across the Sistrugi, so these really uncomfortable ridges that form on the top of the ice sheet, and they're trudging in to this wind because they're actually walking into that katabatic, and they're just getting blasted by ice all the time. And it's not ice that's falling from the sky, it's just ice that's being removed around in their wind. And so where there are exposed pieces of rock, we can see vent effects. And this is a little bit in the granite, you can see. And so particularly for some of the windy places like Commonwealth Bay, the winds are relentless.
Oh, wind nó làm mòn.
The other part, of course, is it's a desert. Well, we think of Sahara, as being a desert, but so too is this, because cold air holds less moisture than warm air. That's why you get big fat raindrops in the tropics. And it's so cold that very little vapour is held in that air. So we have relatively few places where we can measure the aridity, and so for the most part we're trying to figure out how much rain or precipitation is falling on Antarctica. You can't put your garden rain gauge out. For one, there's relatively few places where it falls with rain, and so you're trying to catch snow. But because it's so dry, there's a big vapour gradient. You don't sweat in Antarctica. You smell, but you don't sweat. Because it's wicked away from you so quickly because the air is so dry. And so we have to try to figure out other ways of figuring out how much water that's eventually going to ice is being stored there. And so recently the way we did that was with some maths and then satellites and radar, which would eventually help us out. And so what we now can construct is how much precipitation per year falls over the continent. So these lighter colours, the thickest part here, we're under 20 millimetres of rain equivalent a year. Right, then we see the wetter parts maybe up to sort of 1,000 millimetres along the coast there. And so working in Antarctica, you're surrounded by ice, but there's very little flowing water. Now there are rivers, one or two. There are very few. And so for the most part, the experience of working and living in Antarctica is of observing a place where humans shouldn't be. So this is us doing field training, and you can see the polar tents there. This was taken about 20 years ago, still using the same designed tent that Scott used. Big heavy wooden poles, heavy thick canvas, and an umbilical tunnel that comes out. So you kind of go wiggle your way in, you can tie it shut so no snow ice will blow in. But you're acutely aware that if you didn't have the supplies that were with you, there's no food to forage, there's no fuel to burn, you don't have any way of surviving other than what you take with you. And that's quite a profound sense as a scientist, as humans, to how we think about place. Now, I've talked about this a little bit before, and I'll just sort of add onto it, that not all of the continent is covered in ice. That there are what they generously call oases. And so we had some in the Bunga Hills, which is one of those, the box highlighted here. And then we also have some in and around the Antarctic mountains. So we can zoom in on a satellite image of this, and you can see those dark brown areas are exposed rocks. And so you think, great. Here's a place where perhaps you don't quite feel so isolated, quite so separate to the harsh environment. Two personal observations. One, I showed you the picture of the skua, which we occasionally visit. And every now and then, and I haven't put a photo on here, you would come across mummies. Mummified seals that have come up off Collinia near the coast, and they've gone for a little walk up the valleys, and they can't get back to the ocean. There's nothing for them to eat, and so they simply perish in place. And because it's so dry, they are perfectly intact, except for their eyes, because the wretched skuas, it's the only part they can get to. And so these mummified features just stay perfectly preserved. No one really knows why these seals have done it. It's not that many, but you do come across them. The other observation. We were hiking through one of the dry valleys, and I forget which one it is now. And there was tractor marks. In 1957, 58, the geophysical year for science, some Kiwis decided, and the Brits, that it would be a good idea to drive to the South Pole in a Ferguson tractor. They were successful. It's a great story. Sir Edmund Hillary wrote a book about it, and so did the British expedition leader Fynes. And you could still see the tractor tread marks in some parts of the dry valleys. We couldn't think of any other reason why they would be there. Right, so your imprint on that place is also quite profound, that everything that's been left